Welcome back, chemists. So far in our thermochemistry unit, we've talked about the difference between heat and temperature, and we've also talked about how to calculate heat, which remember is H. So when we're looking at a phase change going from a solid to a liquid, you would find heat of fusion on your reference sheet and plug it in here. And when we're looking at going between a liquid and a gas, you'd find heat of vaporization, which again, you can find on your reference sheet. Now, when we're looking at changing not phase, but temperature, you would look for a specific heat capacity. You would use that formula, okay? All of those, remember, can be found on your reference sheet. So today, we're going to talk about the difference between exothermic and endothermic reactions and how to interpret potential energy diagrams. So endothermic reactions occur when there's a transfer of heat to the system. So the reaction is absorbing energy, okay? Where in an exothermic, think exo, exit, it's a change that's transferring heat out of the system. So the reaction is releasing energy. So thinking back to what we know about phase changes, which ones do you think would be exothermic and which ones do you think would be endothermic? Now would be a great time to hit pause and make a prediction. So looking at this diagram, we should know by now that in a solid, the particles are packed close together and just vibrating, where in a liquid, they're moving a little bit more, and gases have even more energy, so they're moving more. So when you go from a solid to a liquid and a liquid to a gas, they're moving more, right? So in order to do that, you need to add energy. So those would be examples of endothermic reactions. Where if you're going the opposite way, you want to slow the particles down. So for instance, a gas going to a liquid, the gas is moving all over the place, where the liquid's still moving but not quite as much. You have to remove the energy. So again, think it's removing, it's exiting. Those would be exothermic reactions. Here's a list. So you can read this on your own, but remember, whenever we're absorbing or adding energy, we want making particles move more. They'd be endothermic reactions. And in the case where we're getting rid of that energy, we're having it exit so the particles slow down. Those would be exothermic reactions. So now we're going to talk about heat of reaction, which is the amount of energy released or absorbed by a chemical reaction. You'll also hear it used the term enthalpy, so they kind of mean the same thing. Again, we're looking at delta H, so it's just another way to calculate heat again. We're looking at the difference between the heat of the products and the heat of the reactants. Remember, if energy is absorbed, it's endothermic, so think absorbed, it's going to be positive, or if it's released, it's exiting the system, it's going to be negative, because it's exothermic. So, going back to endothermic and exothermic reactions, delta H will be positive or written as a reactant if it is endothermic. And if you look at this graph here, there's an example. So notice where the reactants start, where the products end, the delta H is positive. The energy went up. Okay, mathematically, let's call this 5, this 25. Okay, the delta H would be the difference between the two, so it would be 20. How that would be written in a reaction, you can see an example here. You could either write the reaction with just a positive delta H at the end, or you can write the reaction with the delta H written as a reactant. Either way would indicate that it's an endothermic reaction, that energy is being absorbed. Versus in an exothermic reaction, again, it's releasing heat, so delta H will be negative. So if you look at this example, again, we'll just kind of make up some numbers. Let's say we start at 20, we end at 5. 5 minus 20 in this case would be negative 15. You can notice it's going down, okay? How we would write this in an equation, we could either write delta H as a negative value or just write it as a product. Either way would indicate that it's exothermic. So a practice problem would look like this. You'd be given equations and you would have to identify if it's exothermic or endothermic. So looking at number 1, I noticed that the delta H is given as a reactant. So in this case, it would be endothermic. It's positive, it's written as a reactant, that's showing that it's being absorbed in the reaction. Versus in number 2, it's written as a product, which means it's being released, so that would be exothermic. Now, if you look at number 3, it's not in a product or a reactant, but I notice that it's positive. So in this case, again, that means it's being absorbed. It's going to be endothermic. If that was written as a negative number, that means it would be released, which means it would be exothermic. So now we're going to talk about potential energy diagrams, which is a way to look at this graphically. We've already talked about the heat of reaction being the energy difference between the products and reactants, but now we have to look at something called activation energy, which is the energy different from the reactants to the highest energy point. Think of it as the energy required to get the reaction moving along. Okay, you might also hear it be called the activated complex. Now, you can lower this with something called a catalyst. You might be like, hey, Ms. Gutierrez, I've heard of a catalyst. Yeah, that's why I call your warm-up bag, because the idea is it gets you going, it gets you thinking. So let's look at an example of a potential energy diagram. The first thing I notice is the delta H, the heat of the reaction, which again is looking at the energy difference between the products and the reactants. In this case, you'll notice it's going down, so it's negative, which means it's an exothermic reaction. The next thing I notice is the activation energy. Notice there's two of them because it's showing the uncatalyzed versus catalyzed reaction. Remember, a catalyst lowers the activation energy. So I'll do it in green so it's a different colors. So the energy to get started to the highest point for the uncatalyzed reaction is much higher than, we'll go in yellow for the catalyzed reaction. Okay, and you might be like, Ms. Gutierrez, why are you starting that middle line? Remember, we're looking from start to highest point. And that's for what's called the forward reaction. If we wanted to look at the reverse direction, so going the opposite way, and in this case, notice it's ending higher, so that would be an endothermic reaction. We'd look from the bottom. So for the catalyzed reaction, it would be that high, versus for the uncatalyzed reaction, it would be much higher because it's requiring energy. So it might be a little easier for you to see once we put some numbers on this, but just think of when I'm talking about activation energy, you're looking from the starting point to the highest point. And remember to pay attention if we're looking to the forward reaction or reverse reaction. So now we're going to put some numbers on it to do a practice problem. Problem A says, what's the delta H for the forward uncatalyzed reaction? So again, delta H is looking at the difference between the product or reactant. So this value right here, we'll just put an H so you can see. Okay, because we're starting here at 150 and we're going down to 100. So in that case, 100 minus 150 would be negative 50 kilojoules. Okay. Next, it says, what is the delta H for the forward catalyzed reaction? Notice it doesn't change. So even though there's a catalyst here, the delta H is not changing, so that would also be negative 50 kilojoules. Okay. However, now we're going to look at the reverse reaction. So going the opposite way, in this case, we're starting at 100. I'll change to red. We're starting at 100 and we're going to 150. So 150 minus 100 would be positive 50 kilojoules. Okay, because you're going the opposite way. Same for D. The catalyst is not changing the delta H, that just changes the activation energy. So that would also be positive 50 kilojoules. Okay. So in that case, when it's asking about the forward reaction, if it's endothermic or exothermic, the forward reactions were both negative, so that would be exothermic. Okay. Now, if we're looking at the reverse reaction, those were positive, so those would be endothermic. So that's how you would get delta H off a potential energy diagram. If you're not sure how I got those numbers or why some are positive and one are negative, I would pause and rewatch that section before going on. Because now I'm going to show you how to get activation energy. Remember, the higher point is showing the uncatalyzed reaction, so I'll put a U, and the lower point is showing the presence of the catalyst, so the catalyzed reaction. So we look at question G. It's asking for the activation energy for the forward uncatalyzed reaction. And remember, to get your activation energy, you're looking from the start to the highest point. So there. So in this case, it would be 300 minus 150, which equals 150 kilojoules. Again, how I got those numbers, I'm looking at the difference from the highest point to the starting point. Now, when I look at the catalyzed reaction, I'll switch to red here. Again, my highest point is different. So I'm still starting at 150, but this time I'm only going to 250. So in that case, I'd find the difference, 250 minus 150 equals 100 kilojoules. Sorry about my handwriting being a little off today. My screen's not cooperating. So that's the forward reaction. Notice those were both asking about the forward reaction. Now we're going to look at the reverse reaction, so going the opposite way, because both of these are I and J asked for the reverse reaction. So I asks for the activation energy for the uncatalyzed reaction. So in this case, we're starting at 100 and going to 300. So 300 minus 100 equals 200 kilojoules of energy. Fix that for you. Okay, where J asks for the reverse catalyzed reaction, so we're still starting at 100, but this time we're only going to 250. So you'd have 250 minus 100, which equals 150 kilojoules. And these are all in kilojoules, because remember, that's what we look at, delta H in joules or kilojoules. So that is the difference between an endothermic and exothermic reaction and how to interpret a potential energy diagram. I know this can be a little tricky with the diagram, so I recommend pausing, maybe rewatching, rechecking your notes before going ahead and moving on to what's next. So have a great day, chemists.